Well, the motivation of this work is to deal with the problem of unsupervised image segmentation. Typically, you have images, natural images like this one, and you would like to find the regions, the more relevant regions, automatically of the image. Indeed, this is one of the most relevant problems in low-level computer vision, since when you are detecting the regions, you can try to identify the object and these kind of things which are done in computer vision. And there is a huge state-of-the-art on image segmentation. Many methods in image segmentation will start from the norm of the gradient of the image. And typically, this function will give you a local estimate of the strain of the contours of the image. And then from this one, you will try to minimize any kind of functional related to the image and try to find the contours which define the object of your image. Here, I am interested in one of the segmentation approaches which are available in the state-of-the-art, which is called the stochastic watershed, which will produce from the gradient image, from the previous image, this kind of probability density function of contours. And then, from this kind of hierarchical representation of the strain of contours of your image, you can cut at a given level, and you will obtain now a hard segmentation of the image. And according to the threshold, I will not go into details how the cut is done. It's not only thresholding the probability, but nevertheless, there is a parameter which appears there. And according to the parameter you have, you can select more or less contours of your image. The problem is, as the original source of information for the segmentation is a local information given by the gradient, you can have some problems in the areas when you try to reduce the number of regions in the areas where the gradient is relatively low, locally. Okay, so a way to try to improve these kind of things is to introduce a more regional information during the segmentation procedure. In particular, in our case, in the case of the stochastic watershed. So this is more or less the context of the work. According to these different paradigms of segmentation, on the one hand, we have approaches which are based on a kind of a statistical modeling of pixels. For instance, in the previous talk, it was a typical case. Other approaches are, as the one I just showed you, more based on contour detection. So the goal is try to combine both approaches, or at least to try to introduce in the contour detection-based approaches a more regional information. So in our case, in the estimation of the probability density function by the stochastic watershed. And in fact, we will use very simple assumption about the distribution of the regional information, which will be a Gaussian model, which will make things much easier. Okay, so before introducing the contribution of this work, let me give you a very brief reminder of how stochastic watershed works using Monte Carlo simulations. And the first ingredient we need for that is the notion of random markers, which will be used for the segmentation. And we will use as markers a Poisson point process, which in the case of a uniform density of the process is equivalent to simulating the point independently and uniformly or on the domain of the image. Here we're more interested on the notion of regionalized random point, which will depend now on a density which is variable over the space of the image. And in such a case, when you have a now the density of point theta is a function of the space, of the domain of the image. And according to that, if we have this density function, we will have a distribution of points where the parameter of the Poisson distribution depends on this function. In practice, you can use different algorithms to simulate the endpoint, which will be used just now in the simulations, following this particular density. Okay, for instance, one of the simplest way to do that is to use the inverse transform sampling in order to generate a given number of points following this spatial regionalization given by theta. Okay, so what is the idea of the stochastic watershed? So watershed is one of the most popular approaches in segmentation, and typically in the classical way to use a watershed, you will introduce some deterministic markers for your image, which are related to the important regions. In the case of the stochastic watershed, we replace these deterministic markers by random markers. But now, instead of doing a single segmentation, we will consider a certain number of realization of this segmentation by random markers. And then, by a Monte Carlo procedure, we will try to estimate, by this way, how relevant each piece of contour, depending on the number of times the contour appears during the simulation procedure. And the key point is how to simulate the random markers. You can take uniform markers, but in practice, it's more interesting to consider random markers which follow a density which is related to the image gradient of the image. Okay? So this is more or less the procedure, more formally how that will work. So given an image, when you have your color gradient has been computed, you will simulate a certain number of realization of random markers following the density of related to the gradient. For each one of the realizations, you will compute the Watershed transform of this of the realization according to the random markers, and you will take the indicator function of the result of this simulation, and then you will estimate the probability density function by a Parsons window method using this this result of each one of the realization. So I can illustrate a little bit more on images. So original image, typically a color gradient from the image. And we simulate, here I show you 3 examples of realization of random points. We need to fix typically the number of points. And here you have 3 realization of this point. And here you have the corresponding Watershed transform from these random markers on the gradient of the image. And by changing the markers, you obtain different segmentation. And as you can see, some of the contours are stable independently of the position of the markers, where other less relevant contours will oscillate, will be more stochastically filtered out during the different realization. So by integrating this kind of realization, you will estimate this kind of probability density function. And this is the same example I showed you at the beginning. And this is, again, one cut you can obtain at a given value of probability or a second one. Okay, so this is the classical way to do these things. So now the contribution, the idea is quite simple. What can we do in order to have something much more regional? So let me first come back to the representation of the image, which is obtained from each one of the realization of segmentation. So the Watershed transform produce something we call a tessellation. As you know, a tessellation will be on this domain, which correspond to the image. A tessellation is a finite family of disjoint set, which correspond to the regions, and the boundaries of this open set correspond to the contours between the regions. So in other terms, between any pair of regions after the segmentation, we have an irregular arc segment which define the contour between the two regions. Okay, and we will use these boundaries between any pair of regions as the support where we will weight a distance between the regions. This is the idea. For example, idea, now we will model each one of the regions of the image by, we consider they will be represented by a multivariate normal model. So that means we will compute for each region the mean, the color mean, and the empirical covariance matrix. And now, as I said, we will consider the boundary between the two regions is weighted with a function which depends on the distance between the normal distribution for each one of the regions. So the assumption of Gaussianity is more or less justified in the sense of the result of each one of the segmentation during the procedure will produce regions which are quite homogeneous. So the color in the region is quite homogeneous, so we can expect that can be relatively well formalized by a normal distribution. And finally, the thing we need here, the unique ingredient which is missing, is the distance between two multivariate normal distribution. So in the state of the art, there are a few of them. The two which are related to the information geometry community are, on the one hand, the Batacharaya distance, which is well known here in our community, which is the expression for the normal distribution is we have a closed expression for that. So the Batacharaya, in order to be precise, is a distance, is not a metric. We have a problem with the triangle inequality, so we can consider an alternative, which is the Highlander metric distance, which is related to the Batacharaya one, and which is also important very important in information geometry, as you know. And another alternative of distance between normal distribution, which has a closed form, comes from another domain, from optimal transport, which is the Wasserstein metric distance, which in the case, again, of multivariate normal distribution has a closed form. And in fact, for us, it's important to have a closed form for the efficiency of the algorithm. Remember, we need to simulate, in the Monte Carlo procedure, we need to simulate a certain number of segmentation, and for each one of them, we need to compute between any pair of regions in the segmentation, the distance between the regions. So it's relatively costly, and at least we need to have a closed expression which makes things more easier. So now the procedure will be as for the standard stochastic watershed, but we will replace, instead of having the indicator function of the lines, of the contours, now we'll have a weighting function which depends on the distance between the Gaussian distributions. And then we will integrate again, and we will estimate the probability density function. So in order to compare with the previous example, these are the realization of segmentation which were obtained for 3 given realization of markers. And now here is the corresponding weighting function, where now we replace here each piece of contour by the distance between the two corresponding regions which has been modeled by the Gaussian distribution. So, and we can apply for any of the previous distances, we can compute the corresponding density of contours, and of course to obtain the segmentation. So here, for instance, is the example for the Batacharaya distance. So this is the color gradient, and this is the corresponding probability density function, which is related to this distance, and one of the thresholds which can be obtained from there. We can consider Highlander distance or Wasserstein distance, or for instance another distance which consider only the means. instead of having the full Gaussian distribution considering the mean and the covariance matrix. And something which appears clearly from this example and other examples is the Watershed distance, where the computation of the distance is done separately for the means and for the covariance matrix, is less significant. I mean, the information given by the covariance matrix is less significant than in the case of Bhattacharya or Highlander. And we can think we are running short on time, so we'll try to finish. So we can now compare that. I think I can skip more details. And this is a comparison with another approach which also uses statistical modeling of regions, but it's not relevant for us. So let me conclude more on the perspective than on the result of the approach. So in fact, something which is clear is in the previous approach, I am only using color information. You can easily introduce and combine with texture information. That will be another, for instance, Gaussian or another representation of the region, which can be also easily integrated in the procedure of estimating stochastically the contours of the regions. And something which is relevant for the problem can be if in the case of the color images, we're estimating a covariance matrix, a 3x3 covariance matrix, which is estimated sometimes from a relatively small region. That means the number of pixels available to estimate the covariance matrix can be relatively small. In the case of multispectral or hyperspectral images, where we can apply the same approach, estimating the covariance matrix can be more difficult in terms of the number of samples which are available. So this is something already to take into account. And this can be also combined with a learning approach where instead of having standard distances as Bhattacharya or Highlander, we can learn previously the distance and then to use the distance which has been learned or a particular geometry learning to that. Okay, thank you for your attention.
Talk. So, some question?
One important problem is to obtain the region which are in the first place and not interrupt by something which is behind.
Okay,
it
you
seems
mean the depth of the scene?
Yeah, for example, the tree has to be uninterrupted, and it seems that the results are not the same for the different distance.
Yes. And now, in fact, in computer vision, they usually try to combine the color information available from the scene from the geometry of the scene. I mean, with some acquisition device, Kinet cameras and other ones, you can have the first plane of your scene, the things which are close to you and the things which are far. And that can be really easily introduced here. I mean, you can have a prior in the number or in the density of points you will introduce during the simulation, which will depend on how close or far are the things on the scene. This was your point?
How from the first contours you determine the regions? when the regions are determined is okay, but the first step, how
Yes.
from
So the first step, I don't know if you are familiar with Watershed transform. So basically, between, let me find here. So in the Watershed transform, from the, we have something we call the floating function, which is the function which will be used during, let's say, the minimization procedure, which in our case is the gradient. And when you have a set of markers, like this one, you will obtain for each one of the markers a region. And this region is defined as the locus of the points, which are the lowest value, the highest, sorry, we take the gradient, the highest value in the short path connecting the two markers. So this is a kind of min-max optimization, which is done from here to obtain this one using the gradient. Usually, the efficient algorithms use a graph representation of the image, and everything is done on the graph of the image.
Other question?
Okay.
Okay, I don't know if it's interesting to consider a penalization term in terms of surface of region over you compute the,
Yeah,
the statistics.
Yes, that can be done. During the computation of the Watershed, you can remove the regions which are too small. You can have a prior on the corresponding region. And during the flooding procedure, regions smaller than a given threshold are not, will not be segmented. Yes. And that can be relevant when you need to estimate a covariance matrix and you need to have a certain number of samples for each one of the regions. Yes.
To obtain an evaluation, objective evaluation based on the something like grand truth about the
Yes,
the limit of region.
I didn't assess the performance of the segmentation, but there are some databases which are available, which can be done, which can be used to evaluate that. I didn't compute for a set of images and then try to compare, because there is a ground truth segmentation doing by hand. We can compare different approaches on this database. Yeah, I think we are bringing that.